Hi everyone, we're going to have a look at the homework questions from March 24th. Now I'm going to do this video in two sections. If you did the questions that were attached to the PDF, the ones about the acceleration due to gravity and this one about the spacecraft, this is the video for you. If you did the one that I had inadvertently given you the wrong questions, the one about the latent heat of ice and the thermistor, I'll do that as a second video so you can safely kind of leave this one, but it might be worth having a look at anyway. Okay, so the questions that I'd originally set. In an experiment to measure the acceleration due to gravity, the time t for an object to fall from rest through a distance s was measured. The procedure was repeated for a series of values of s, and the following data was recorded. Draw a labelled diagram of the apparatus used in this experiment. Okay, so this is the one involving the electromagnet and the electronic trapdoor. Now, I'm going to not make this an artistic masterpiece, but I am going to label everything. You don't get any, be neat and be thorough and be detailed, but you don't have to spend 20 minutes doing an absolute masterpiece. So there's my retort stand. But you do have to label everything and show clearly how you'd obtain your data. So on the retort stand we had an electromagnet. I'll label it after, actually, it's probably easiest. We have a trapdoor, an electronic trapdoor, which isn't like a trapdoor like you think in movies. It's just, it registers an impact when something hits it. That was connected to an electronic timer. And there was a ball bearing attached to the magnet, and we had to measure the distance between the ball bearing and the trapdoor. For that we used a meter stick or ruler. Now straight away, label everything. Sorry about the smudge here. I'm going for speed here. Label everything. Presume that the person marking your test doesn't know anything. So label absolutely everything. Timer, retort stand, electromagnet. Should have that in red. Ball bearing. Just that metal ball. Meter stick or ruler. And the trapdoor. Yeah. I don't know how long that took, but let's say less than 4 minutes. Possibly 5. For close to 15 marks, it's probably going to be like 12 marks on a leaving cert question. So definitely worth knowing the experiments inside out and making sure you label absolutely everything. Now, have I labeled everything? Like a giant hypocrite, did I miss something? I don't think so. Okay, so let's remind ourselves what happened in this experiment. We were trying to measure the acceleration due to gravity, which we know just from doing it loads of times in different calculations, it's going to work out as about 9.8 on Earth. So we have to kind of find that out experimentally. Okay, so what we did was we had an electromagnet, which is a magnet that is only a magnet when there's current running through it. We had it connected to a timer, and the timer was also connected to an electronic trapdoor, which registers when the ball hits it. So what happens? We turn off the power to the electromagnet, and two things happen simultaneously. The first thing is that the ball is released, because it's no longer held by the electromagnet, and it starts to fall. The second thing is the timer will start counting up from 0. A few seconds later, the ball will hit the trapdoor, which will stop the timer, giving you the time it took for the ball to fall a known distance. And now we're kind of back onto the question part. So draw a label diagram, done. Between which points was the distance s measured? Well, it was measured from the bottom of the ball to the top of the trapdoor. Describe how the time t was measured with an electronic timer. Now there's 15 marks on leaving cert question very, very quickly. They're going to make us work for the last chunk of change though, so let's see. Draw a suitable graph that can be used to determine the acceleration due to gravity and hence determine g. Alright, well, before we get into it, let's check this question for traps, because there is a couple. The first trap is they give us let's look at the units. We know that centimeters is not our best buddy when it comes to units, meters is. So we're going to have to convert these centimeters into meters just by realizing that 1 meter is 100 centimeters. Now, I've done this very neatly in a moment, but very quickly, that would be 0.30, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. Quick point to note here is drawing on your question sheet does absolutely nothing for you. Make sure if you're converting any units or doing any manipulation like this, do it in your answer booklet, I beg your pardon, so that the examiner can see it. They don't see this booklet of questions. They never see that. They only see your answers. So make sure, however irrelevant you think a calculation might be, lash it in. Not irrelevant, but however, if you think it's not that necessary, put it in anyway. Okay, so on that note, I've converted the units just for the sake of time, because now I'll come to this t squared in a moment. So first off, convert the the distance measurement to meters, 0.3, 0.4 meters, 0.5, 0.6. They've also laid a trap here by giving us the time in milliseconds. Now I know I'm kind of zoomed out here, but you've got the question in front of you, so that should be visible. And 1 millisecond is 1,000th of a second, or 1 by 10 to the minus 3. So we need to convert that too. So here, 250 milliseconds is 0.250 seconds, and convert it along. Now, onto this t squared. Right, we need to take a little bit of a theory, a nosedive into some theory here before we crack on. So, if you were tempted to just lash right into doing the graph, you might do a graph of S versus T in either direction. Unfortunately, that's not the way to go. Now, to realize why that's not the way to go, let's look at graphs in general. All right. Now, by the way, I'm doing a very speed run here. The first 10 pages, I think, of your experiment book. So your experiment books, the white book of experiments, is an invaluable resource. Make sure you're using it to go over the experiments associated with each topic as you revise. But the first 10 or 20 pages summarize all the kind of maths and graph skills that are involved in each experiment, which is where a lot of people fall down. Now for this one, at first glance it looks easy, but it's really not. Now let's start by looking just at graphs in general. If I get the slope of a graph, which is a very useful thing to get, it's usually rise over run. Now let's think about what we've got here. We've got displacement and we've got time. Now let's think back to our constant acceleration equations, the Suvat stuff. I'm going to start with S is equal to ut plus half at squared. Now you don't have to do this in the question, this is just explaining why it came about. So if you remember, in relation to our experiment, we're dropping a ball from that electromagnet. At first, its velocity is 0. So we can get rid of this whole part of the equation. Displacement is equal to, because this initial velocity is 0, it's just equal to half at squared. Now I'm going to write, instead of a, because we're looking for acceleration due to gravity, let's just put in the little g instead of a. Same thing, but we're in relation to Earth, multiplied by the square of time. Okay, let's rearrange this. We're looking for the acceleration due to gravity, so let's get that on its own by just rearranging this expression. So I'm going to bring the 2 across, giving me 2s is equal to g t squared. And now we're looking for g on its own, so bring the t squared across, multiply by there, divide by here. 2s over t squared is equal to g. Okay, now let's think back to our graphs. So we're looking for acceleration. Now if we were to graph s on the y-axis and the square of our time value on the x-axis, now we've got a situation where the slope, the rise over run, s over t squared, will give us not quite gravity, but it will give us half of gravity, because twice the slope is the acceleration due to gravity. Now that was quite a lot to digest in a short space of time, so make sure you're going over this as you're revising forces and acceleration. But that's why this is going to be useful, squaring the t. Now to speed things up a little bit, no pun intended, I have done that for us. And I'm going to focus on graph work for the next few minutes. Now if your graph work is completely solid, you can skip on to skip forward until I've done the graph. But let's have a gander at how to do graphs, because this is where people struggle quite a bit. So the first thing to realize is how much space, how much space you have and what data you have to accommodate. So the distance measurement goes from 0 up to 0.9 meters. That's the maximum value you have to accommodate for distance. The t squared effectively goes from 0 and it goes up to 0.189 seconds squared. So that's the value you have to accommodate there. Now your typical graph paper has, I think it's 9 big boxes in one direction, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 in the horizontal direction. Now, don't agonize too much over this, but the thing you want to do is make sure that whatever axes and scales you choose, you've got enough room to accommodate all your results and that your graph isn't squashed down into one corner. You want it to take up a decent chunk of the page. You also have to leave room for your labels. So let's get cracking. Okay, we're going to put S on the y-axis, so to go up to 0.9, and we're going to go on the x-axis 0 to 0.189. Now, I've chosen to do this landscape, and because just by happenstance, 1, 2, 3, 4, we can go up. If we've got 9 boxes vertically, I'll do mine in pen just so it's a bit more visible on the screen. You should read yours in pencil on the day. That way, if you make any mistakes, you can cross them out, or sorry, erase them. Just zoom a little bit more here. So we're going to have our displacement on the y-axis, which is in meters, and on the x-axis we're going to have our t squared, which is in seconds squared. That's the unit. Bit confusing there, but time squared in seconds squared. Okay, so we're going up. If we were to go up to 0.9 meters, each big box here is going to be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, and 0.9. Going across, we have to accommodate, now here's where, sorry, that's off the page. We have to accommodate, the biggest value is close to 0.2, okay? So that way, what I'm going to do is I'm going to take each big box, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to make that 0.200. Now I'm going to make it go up in 0.02. Every big box is going to be 0.02. So that's 0, 0.02, 0.04, 0.06, 0.08, 0.10, 0.12, 0.14, 0.16, 0.18, and 0.20. Okay, let's plot our points. And again, for the sake of speed, I've got them here. So we have, when displacement is 0.3, our t squared value is 0.625, so that would be 7, so it would be about a quarter of the way, roughly there. Here's the first data point. Our second one, 0.4, with a value of 0.081, so that's about there, approximately. 0.5 meets 0.0961, so about there, give or take. 0.6 to 0.119, so that would be 0.11, 0.19 would be about there, maybe a little further to the right. 0.7 goes to 0.144, which is about there. 0.8 with 0.16, that's nice and even on the line there. And 0.9 with 0.189, our biggest value, which is 0.18, it's kind of close to here. Okay, so there's our data points. Now this graph will be directly proportional, because if you have a distance of 0, the time taken will also be 0. So our graph will go through the origin. It doesn't always, but this time it will. Now a line of best fit, you don't try and join up all. If you try to join up all these lines, it would just be a zigzag, be a mess. Try and go for the line that best fits most of the data. So I think it's about there. There's my line of best fit. Now let's just have a quick check at it. It goes through one of the points, but it goes quite close to the rest. This fellow here might be a bit of an outlier. It looks like quite a little bit off the graph. Okay, that was just kind of graph practice skills in case you were rusty. Let me find a question. Would be helpful. Okay, draw a suitable graph to determine the acceleration due to gravity g. Boom. Hence determine g. Okay. Well, earlier, let's do this on here. That's good. Earlier we said that if we were to rearrange this, we'd have g is equal to 2s over t squared, or that g is twice the slope of this graph. So we need to get the slope of this graph. So let's go m is equal to y2 minus y1 over x2 minus x1. And again, these are from your logbooks. Get familiar with them. They're in the coordinate geometry section. Now, you can choose any 2 points to do your graph. Oh, look at that nice fella there. Right through the crowd. That's lovely. There's one. You can choose any 2 that are convenient. Decent bit of distance away from each other. I'll go with that one. And I'll go with this one. Looks nice and handy to do as well. So let's just write out which one is which. This is going to be my x1, y1. x1 is 0.04 seconds squared. And my y1 is 0.2. And for my second data point, we'll say over here, isn't it? It's 0.16 and 0.8. x2, y2. Okay, let's plug them into our formula. y2 minus y1, so 0.8 minus 0.2 over x2 minus x1, so that's 0.16 minus 0.04. So that's going to be 0.6 over 0.12. So that's going to work out as 5. Let's just check. Trust your calculator if you don't trust your brain on the day, because you're going to be under pressure. 5, lovely. So our acceleration due to gravity was 5. Sorry, not acceleration due to gravity. The slope of our graph was 5, and twice the slope is 10. So we've got a calculation of acceleration due to gravity is 10, which is reasonably close to the 9.8 that we know it should be. So they definitely made us work for those. Now, again, that's just practicing graph work. If you're a little bit hazy on it, go, make yourself go through the questions, go through the graphs, do them. Don't just presume it's easy to do. Physically do them. Okay, hence determine G, sorted. Finally, a small dense ball was used as the object in this experiment. State an advantage of using this type of ball. Well, it's small, it's dense, there'll be minimal air resistance just down to the shape of it, because it's a ball. So you'll minimize air resistance by using that. Okay, so that was the first question, which was experiment based. Second one is theory. So let's have a go. State Newton's law of universal gravitation. Okay, well, first off, it's in your logbooks, right? You just have to find it. So when I'm always harping on about becoming familiar with these guys, let's just find acceleration due to gravity. They're usually around page 54, 55, 56. There we go, 56. First, I'm going to write out the equation. Now, this wouldn't be enough to get me the marks, but it's a good start. Okay, so there's the equation. We have to say what each bit is. Otherwise, it's just copying from the logbook. So here, it's the force of gravity is the gravitational constant times the mass of the first object times the mass of the second divided by the distance between them squared. You could also phrase this as the force is proportional to the product of the masses and inversely proportional to the square of the distance between them. Use this law to calculate the acceleration due to gravity at a height above the surface of the Earth, which is twice the radius of the Earth. Okay, now we don't have to derive this next part where I'm going next, but I will just for the sake of it. We're going to say that acceleration due to gravity is gm over d squared. So how does that come about? Well, we're talking about acceleration. And acceleration is mass times acceleration. Sorry, force, I beg your pardon, is mass times acceleration, which is the universal gravitational constant. We're going to use a capital M to represent the mass of the Earth, with the Earth being the first object we're talking about, and a little m for the mass of the object that's going to be accelerated, in essence, divided by the distance between them squared. So we have a mass on both sides. So the acceleration, which is really the acceleration due to gravity, is equal to gravitational constant times the mass of the Earth divided by the distance between them squared. Okay, so what do we know from this question? We've got the Earth and the radius of the Earth. You'd experience a gravitational pull of 9.8 from there. But they want us to find out what would be the gravitational pull if you were up in the air at a distance that was twice the height above the surface, which is twice the radius. Okay, so if that's the radius, we're twice the radius above it. So this would be 3 r's above it. R. So at a distance of 3 times the Earth's radius, what happens to the gravity? Now here what they're really asking you to do is to show that you understand how an inverse square law works, where the acceleration due to gravity, when you double the distance, it doesn't go down by half. The gravity force doesn't go down by half, it goes down by a quarter because it's the square of the difference of the distance. So here, we've gone from 1 Earth radius to 3 Earth radii. So it's gone down not by a third, but by 3 squared. So the gravity at this point will be 1/9 of the gravity that you'd experience here on the surface of the Earth. So use the law to calculate which twice the radius. All we're going to do is multiply our 1.9 by our known value of 9.8 meters per second squared. So it will be 1.08 meters per second squared. Okay, they're definitely making this work a bit harder for the points here. A spacecraft is carrying some stuff. Spacecraft carrying astronauts is on a straight line flight from the Earth to the Moon, and after a while its engines are turned off. Explain why the spacecraft continues on its journey to the Moon even though the engines are turned off. Because the acceleration given to the rocket will continue to propel it forward. There's no other forces slowing it down. There's no air resistance. And if it's escaped Earth's gravity isn't pulling it back, or if it is, the Moon's gravity is overbalancing it. So it'll keep going until an external force acts on it. Describe the variation in weight of the astronauts as they travel to the Moon. Okay, well, let's walk through their journey. As they start off on Earth, they have a maximum value of weight in the locality because they're very strongly attracted to the Earth. Aren't we all? Then as they launch off, they go more and more distance from the Earth. So their gravity, their weight, I beg your pardon, is going to go down. Eventually we'll reach a point where the gravity from the Earth is equal to the gravity from the Moon, and they'll experience weightlessness, where they have no weight whatsoever. They don't experience any weight. Then finally, as they get closer and closer to the Moon, their weight is going to increase again until it reaches whatever the value is on the Moon. So to summarize, their weight is going to decrease, it'll reach 0, and then will increase again until they reach the weight that they'd have on the Moon. At what height above the Earth's surface will the astronauts experience weightlessness? Okay, starting to get a bit trickier now. So when you experience weightlessness in this situation is when the gravitational force from the Earth is equal to the opposing force from the Moon. The gravity pulling you towards the Moon, the gravity pulling you from the Earth will be equal, so you have no weight. So let's see what they are. So let's go back to our acceleration due to gravity. So that's gm over d squared. And let's put a few prefixes in here. E for Earth, gravitational constant is constant. Mass of the Earth, the distance to the Earth, versus the Moon. Gravitational pull of the Moon. So this should be a little g really. The gravitational acceleration due to the Moon. Gravitational constant times the mass of the Moon divided by d squared. Okay, let's equate these two. G, mass of the Earth, I'll try and get a bit neater as we go actually because it's a bit messy, divided by the distance to the Earth squared is equal to gravitational constant, mass of the Moon, divided by the distance to the Moon squared. Okay, well straight away, universal constant just cancels out. Now what are we looking for here? We're looking for how far from the Earth we are. Now to be a bit sneaky here in the question, they don't want us to fully calculate things. They tell us that the no, they don't. Okay. Oh, they do it as the radius of the Earth, acceleration due to gravity. Ah, there we go. I knew I missed something. Assume the mass of the Earth is 81. Here's an object lesson. Read the question carefully. Assume the mass of the Earth is 81 times the mass of the Moon. Okay, so the mass of the Earth is 81 times the mass of the Moon. Let's rearrange this to get the distances on one side, the masses on the other. So let's cross multiply me d squared mass of the Moon is equal to m d squared e. So the mass Earth times, let's bring the mass of the Moon across. So me over, I'm doing this kind of in long drawn out ways. I know many of you will be more comfortable just doing it kind of quickly. That's fine. Bring this foot across. So all I've done here is equate the two forces, two accelerations, cancel out the universal constant of gravity, and then rearrange this to get the ratio of the mass of the Earth to the mass of the Moon, because that's a given quantity in the question, to the distances involved. Now they tell us that the mass of the Earth is 81 times the mass of the Moon. So this will cancel out and just be an integer of 81. So 81 is equal to the distance to the Earth squared divided by the distance to the Moon squared. So it'll break down the distance into a ratio. So let's get rid of these squares. Let's get the square root of both sides. That'll give me 9 is equal to the ratio of the distance to the Earth to the distance to the Moon. Okay, so it will be when you are 9 times closer to the Moon than you are to the Earth, is what they're saying here. So let's take the distance between the Earth to the center of the Moon, which they give us in the question, 3.84 by 10 to the 8 meters. Now we're being extra sneaky here because they say at what height above the Earth's surface. So what they really mean here is when we get our distance between the center of the Earth and the center of the Moon, which we're going to get in a moment, we have to also realize that we're only looking for the height value. So we're going to have to subtract the radius of the Earth. So we have our 3.84 by 10 to the 8 is the distance between the center of the Earth and the center of the Moon. We're looking for 9/10 of this. Okay, that's the distance from the Earth that we need to do. So let's divide this, let's put the number into the calculator first. 3.84 times 10 to the 8. Let's divide that by 10, multiply by 9. So that's the distance we'd be from the center of the Earth, but we need to also subtract the radius of the Earth. So that's minus the radius of the Earth, I'm going to put it in brackets, is 6.36 times 10 to the 6. Gives us an answer of 3.39 by 10 to the 1, 2, 3, 4, 5, 6, 7, 8. 10 to the 8. And don't forget your units, meters. Right, a lot of work in that question. It looks quite friendly at first glance, but not quite that good. Or not quite that nice. But handy enough, as long as you're diligent. Okay. The moon orbits the Earth every 27.3 days. We've done the lion's share of the work now. This is just going to be the addendum. famous last words. 27.3 days for the moon to go on one full course around the Earth. Moon. Okay, what is the velocity expressed in meters per second? Okay, well, what we're looking for here is the distance that it travels in meters and the time it takes to do that in seconds. So let's deal with the distance first. Well, we're told that the distance from the Earth to the Moon is 3.84 by 10 to the 8. So you can treat that as the radius of the circle. Now, we know it's really an ellipse, but the circle is a close approximation. So the path it takes is the circumference of the circle. And the circumference of a circle is 2 pi r. So it's going to be 2 by pi by 3.84 by 10 to the 8 meters. That'll give us the distance travelled. Now, we'll do this all in one fell swoop. So let's get the days first. If it's 27.3 days, we need to get that in terms of seconds. So there's 27.3 days times 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute. So let's do 27.3 times 24 times 60 times 60 gives us this number, 2358720. And I'm going to divide that into this. So 2 multiplied by pi multiplied by 3.84 by 10 to the power of 8. And I'm going to use a trick here. I'm going to say divided by the answer that we just calculated before. Gives us a velocity of 1022.90 meters per second. Okay, finally, why is there no atmosphere on the moon? Because the moon doesn't have enough gravity to retain the molecules of the atmosphere. They'd just be lost to space. Right, a lot of work in that second question and a lot of practice graph work. Again, keep cracking on with the homework questions. Let me know if you're stuck on anything. And as I say, if you did the latent heat video, or sorry, the latent heat question, I'll have a video for you soon on that. Okay. Thanks very much and see you soon.